A brake disc is under virtually no mechanical stress when the vehicle is in motion. The only force applied is centrifugal force due to the rotation of the disc, and this creates tensile stress. Under braking, however, the disc is subjected to two new forces. First, we have the force of compression, stemming from the pads being pressed perpendicularly against the surface of the disc. This force, in its turn, is the result of the application of pressure from the brake fluid being compressed by the pistons in the calipers. This force, that reaches high levels when near maximum pressure readings, generates a relatively small load on the discs in comparison with the material's resistance limits. The brake force caused by the pads rubbing against the discs makes it a tractive force. It is the part of the disc that is in direct contact with the pads that undergoes braking, i.e., is subjected to a force opposing the rotating motion, whereas the part of the disc that is not in contact is pulled in the same direction as that of the wheel. As is the case for compression, the tractive force too is well below the wheel's limits. It should be underlined that this limit decreases with any rise in temperature, and greatly so should there be the beginnings of a crack in the cast iron. In such case, checks can be carried out for damage. The occurrence of hairline cracks that can appear following extended use is associated with this type of repetitive stress and is known as fatigue. Thermal stress on the discs is more serious. Indeed, all the energy possessed by the vehicle is transformed into heat when the pads meet the discs, and the increase in temperature at that interface is very significant. Depending on the heat-conducting properties of the cast iron and of the materials used making up the brake pads, it is known that in most cases more than 80% of the heat generated is absorbed by the disc. Cooling the discs well is therefore a key factor in how well brakes work. Cooling takes place naturally due to the motion of the vehicle, but this is assisted greatly by the fact that the discs themselves are rotating in a cool airflow. Depending on the amount of heat to be dissipated, differing solutions need to be implemented to ensure good stopping power. The most commonly used strategies are those of increasing the surface area in direct contact with the airflow and of fitting ventilated discs with suitably sized ventilation ducts and increasingly more efficient shapes.